This is the recording for the Python that was used for calculating these different things, especially talking about that demo that we had for the probability of the children both being girls. So we'll go through a little bit of that, talk about randomness, talk about how we would calculate some of these things. But most of the homework, you actually really don't need much Python. It's really knowing which denominators to divide by when we're calculating these different conditional probabilities. So this demo will be relatively short and just go through some of the key concepts for how you would calculate some of these things. Let's get started. We import our packages. Now, most of these you have seen. Maybe random we haven't really talked about too much yet. And random is a package that helps us create true randomness, which is maybe a theory of is anything really random? But it helps us find more realistic randomness to represent our data from. So thinking about like that Plinko probability, we could use something like this random package to say, generate lots of random examples, and then we could take the sum to find some true probability distribution. So we'll be using random, and I'll talk about an important concept of setting the seed of where your randomness starts, so you can be reproducible to get back to that state of randomness. But first, let's just talk about this random child example that we used in the lecture, talking about either having a boy or a girl. We would use this random. And just as a little bit of more context, this practice problem will not really be seen in the homework. This is just from the demonstration in the lecture to show how we would calculate some of these likelihoods if this was a more interesting example outside of predicting gender of children. Okay, so let's just talk through it. This would provide an answer that is random between 0 or 1, just binary, either 0 or 1. You have where boy, let's say that represents 0 and a girl is 1. But this could be more interesting of like flipping a coin or any other type of binary outcome. We could use this function that will simply just return a choice 0 or 1. And I use Python just to show how we can now go through 1,000 different examples and start to find this true probability. And this is example of that law of large numbers, where we can start to simulate these different outcomes. Okay, so now with what I talked about with setting a seed, which is important anytime you use the random package, you must set a seed if you want to be able to get that same randomness again. And this is really important for making sure your code is reproducible, where a seed, similar if you've ever played Minecraft or any of those games where you start with an initial sequence, it will then build upon that. So if we wanted to have this seed be 42, which is, it's arbitrary, whatever number you make. But if I set this at 42 and I do some randomness calculations, I will be able to reproduce that same exact randomness if someone else set the seed at 42. So that's why it's important for reproducible research, because you could have some randomness that you claimed you saw, but if someone else can't create that same randomness, it might be less of a solid argument if they can't reproduce it. So that's why we set the seed. Okay, so we're running a simple simulation. This is saying, let's run 1,000 different iterations. That's why this is just not even any symbol, because we're just saying, do this 1,000 times. We'll say the younger, we run this random child where we're just producing 0 or 1, and older, 0 or 1. We're saying if the older equated to 1, then we would add 1 to this older girl. And if older and younger both equals 1. So this is really just calculating the different outcomes and saying if the older is 1, say now both the older girl equals 1. And we'll just use these to then sum up the likelihoods after taking these different randomness counts 1,000 times. So these are just our different exhaustive outcomes, where if older and younger are both equated to having girls, since the outcome is 1 and 1, we would say both girls, we would add 1. Or if the older is 1 or the younger is 1, we calculate either girl equaling adding another 1. So just by hitting run, now we have these different counts. Let me first just show you what random child looks like, just so you can see that, where it just returns 0 or 1. And now as long as I keep clicking, it'll keep returning something random. So think of that as just like your random flip of a coin. So if we didn't want to think about gender or something kind of silly like that, we can think of this just likelihood of 1 or 0 happening, and thinking of both times we turn this for younger or older, that they both return 1, or that one or the other return 1. In short, that's what this is saying. But now we get to calculating these conditional probabilities. So now we would say the probability of both children being girls, given that the older child is a girl. And the second one is both children are girls, given that either the first or the second child is a girl. And now we have these different calculations, where we can now start to see just what this randomness showed, where we had out of 1,000, 266 resulted in both turning 1 in this outcome, whereas older girl, let's just see what these look like. So the likelihood of just having 1 being older is more likely. These are just the different breakdowns, where it's more rare to have both being girls compared to having one or the other being a girl compared to the older one being a girl. So this is just to show you how we can calculate these things. And now let's think about the joint probabilities of having at least 1 girl, where they're both girls, or the first child is a girl. And we would divide these all by 1,000. So just by going through these, creating a simulation, we can start to get these approximate counts that are probably more representative of what would happen in real life, because we have this law of large numbers, because 1,000 we could say is a generally large enough sample space. And this was just from that first example in the slide deck. This now relates to that other example where we're talking about determinants of economic growth, where we have these different factors we talked about in class. We talked about this quality of data, or if they're a member of the OECD. So this is just reading in a package that was developed for R, actually, which is just, it has a bunch of really nice data sets, which you can explore by clicking this link, where it tells you a little bit more about them. So I like this package because it'll have a lot of nice kind of real world examples of more messier data than what the textbook might show us. So it's always good just to see what's in this thing by using .head. What's the shape of it? We have 121 countries, where each row represents a different country's GDP, their population growth. But the factors we'll be looking at is OECD and inter, because those are pretty much the categorical variables. It could be interesting to look at oil producing compared to having quality data. But again, just for my own hypothesis, I was curious if countries that are in the OECD have better data quality. So we create this contingency table by using pandas.crosstab. And we have our first column of OECD, our second column of the data. And we first say margins equals false, because I just want to see these things, and we'll start to take the sum across. So this is the most important part when you are completing your homework. It'll look a lot more like this example than compared to what I showed above with the whole children thing. So you really need to be careful about what the denominator is when you're calculating these different marginal probabilities. So for example, if we wanted to take the sum of not being in the OECD, this is the index over here is no or yes, where the columns over here are no or yes for the different features we're looking at. So this could be considered feature A, the top, and considered feature B, this vertical feature. So we take, now I'll just for consistency's sake say for not having quality data. So for feature A, the likelihood of no given is total is 46, what is the total yes. So out of all the 121 countries that were in this sample data set, 46 had not quality data, where 75 had quality data. So now we look at the sum across the rows, which now this is looking if the countries in the OECD. And these different ordering of feature A, feature B is more important just depending on what's the independent versus dependent. So we're thinking that the internet, the data quality is dependent on them being the OECD, because of our hypothesis that if they're in the OECD, then they have to institutionally required to share more data and have better transparency around it. So now we're looking at if they're in the OECD or not, where 99 of these examples are not in the OECD and 22 are. And now we can start to take these conditional probabilities. So in your homework, depending on what it is you're trying to calculate the difference between, we would say, now give me in this table, give me the row. So in the OECD, given that that's yes, that's sum, against when the data quality is equal to yes. So this is, again, in the slide where you're getting these nice slices using the contingency tables to take these sums, and we divide them by each other. So I'd say you should compare this with the slide deck when we started this example. We can also calculate, if we didn't want to do the contingency table, because it's somewhat limited in what you can work with it, or if you wanted to make this equals true, then you'll start to see those sums calculated for you, and you can start to divide by different things. But sometimes that gets a little bit more tricky to know which index is which. So sometimes it's easier just to leave it like that, where for me, it makes more sense to group by these different things. But again, this is just different ways to come out with the same solution. So if we wanted to group by the data quality, we take the sum and divide it by the length. And then we would group by if these two columns together, take the size of them and divide it by the length. And we then have this probability divided by the sum of each category. Because the probability of having quality versus not, we have that in this interprobs variable, and then we would divide the total groupings by these different probabilities. So this is how we could think of these conditional probabilities. For joint probabilities, we would just divide these different concepts together. So take this crosstab table and divide it by the length, and we now have these different proportions. So really, it's just a quicker way of dividing by proportions. But even if you didn't want to use any of these group by things, you can just start to take the sums of these different things and divide it by the right denominator. So I expect in the homework that you will show the calculations you used, really just show what was the numerator, what's the denominator for these different probability outcomes. So one question will have to be to create a contingency table, and then you'll start to divide and add things depending on what it is you're trying to solve for. So one note, just be very careful what it is that you are dividing against, and make sure that the numerator and denominator makes sense for what you're doing. So I always think, use a pen and paper, just start to write out these different tables and draw as much as you can to make sure that the output makes sense when you're thinking the different likelihood outcomes.